So let me get you guys caught up to where we were here, and this would explain why I had no responses beforehand. We're going over the 2018 FRQs. We're just starting with the ones that are going to be on this year's exam, and that happens to be the first few ones in there. So the first question we had talking about was the spacecraft orbiting Earth, as shown in the figure above. We're told its mass and its radius and stuff like that. And I just started making a list of all the possible topics that I could think of that could potentially come in and be useful for solving this first question. So I noticed we have a planet or a spacecraft going around the planet. That to me says forces. They mentioned the word circle, so I pulled up circular motion. The only, a lot of times we're doing this, we're talking about gravity. We're talking maybe about potential energy in a universe sort of scale. We might be talking about angular momentum if we're changing our orbit a little bit. Periods, frequencies, that sort of stuff. Those are kind of all the things that we're looking at potentially using in here. So for that, we're going to dive a little bit deeper in here. And now let's actually start solving this. So the first question said, draw and label the forces, not the components, but the forces themselves that act on the spacecraft. Each force must be represented by an arrow. Okay, so how many forces are acting on our little spacecraft when it's sitting in our orbit? How many forces? Please tell me my audio didn't die again. All right. No, okay, good. Okay, good. And chat goes quiet, and then I'm worried here. Okay, so how many forces on our spacecraft? There should just be one. The only force acting between our spacecraft and the Earth is gravity. Okay, so there's only one force. You're not going to have friction in space. There's no tension. There's no other stuff like that going on. The only force that we have here is our wonderful force of gravity pointing towards the center of our circle. That's the only one that could possibly be there. I shouldn't say that. The other possibility would be like if they say in the question, the rocket engines are firing on our spacecraft to make it speed up or slow down. But otherwise, all we have is gravity. That's our only force in there. Okay, so one force, gravity, plain and simple. That's it. All right. Now, if this was AP exam time and you wanted to get scored for that, that earns you a whopping 2 points. 1 point for it being pointing towards the center, and 1 point for it being the force of gravity, or labeling it something like that. Okay. Now, let's pretend that we didn't know that gravity was the force going on here. We could also figure out, without knowing that it was gravity, that there must be a force pulling towards the center of the circle. How do we know that? Well, because they mentioned we are in a circular orbit. And in order to go in a circle, we must have a force pointing towards the center. In this case, that centripetal force is gravity. Yep. So because they mentioned circle orbit, we know there must be a centripetal force, which in this case is gravity. But even if we didn't remember gravity, we would still get at least some credit for drawing a force pointing towards the center of that circle. Okay, moving on to part 2. All right, so part 2, we're supposed to derive an equation for the orbital period T of the spacecraft in terms of those quantities. Draw stuff below. Don't use your Yep. All right, so let's start off here. I've got a spacecraft going in a circle around the Earth. I've got a force pointing towards the center. I somehow need to get a time out of this. So for this, we really need to combine a couple different equations together. We're going to start, as we normally do when we see the word derive. We're going to start with some basic physics principles. That could be something like conservation of energy, conservation of momentum, Newton's laws for rotation, Newton's laws for linear motion, something like that. And because part A mentioned forces, I'm going to start with forces. I'm going to start with, hey, we have F equals ma. And the only force acting on our object is the force of gravity. So the force of gravity must be equal to ma. And we know we're in a circle. So the acceleration in a circle is v squared over r. And that's good because I've got r in my things that I can use. So it's good that I have that in there. So, and we can expand force of gravity to be big G, mass of Earth, mass of satellite, over the radius squared, and get mv squared over r. So far, so good? Yep, okay. Cool. At this point, we simplify a little bit. Let me get rid of the m's. Let me get rid of one of the r's. And I'll have g me over r equals v squared. So now, this is really useful for some questions. Not so much for this one, though. The problem here is I need to get this time. And I don't have a time in my equation at all. So we've got to go dredge up some knowledge about turning one of these things in this equation into something with time. And I'm going to go way back, way back to the beginning of the year and possibly the very first equation you guys learned about in physics. And that is velocity is a change in x over a change in t. Okay. So now if we think about this, I have my little spacecraft. If it goes around the circle once, how much distance did it cover? All right, and I'll give you a hint. It has to do something with a circle. It is 2 pi r. Yes, it's the circumference. So this went 2 pi r over t. T being the period, the time it takes for one cycle. So now I have this, we plug it in, and now I can actually solve this for t and get my answer. So putting this back together here, I have g me over r. I'm switching to capital R's because that's what I need to have in my answer here. That's all. I'm going to make the mistake and switch back and forth. And it's v squared. So this is 4 pi squared r squared over t squared. And then a little cross multiplying, a little combining terms, and we'll end up with t squared. I need t, not t squared, right? T is the square root of 4 pi squared r cubed over g me. And there is our answer. That is our BI. If you're interested in points for this, this gives you a very nice 3 points. 1 point for using the Newton's law stuff, 1 point for finding the v equals 2 pi r over t thing, and then 1 point for actually getting an answer, which is t equals, sort of stuff like that. All right. questions on the derivation? Oh, okay, cool. This is probably actually one of the more complicated derivations you may be asked to do, just because you have to pull in Newton's laws, circular motion, velocity equation, gravity, and pull it all together. So if you get this one, this is probably the most complicated one that we're going to be able to see in the realistically AP world for this year. Okay, double I. Second spacecraft of mass 2m is placed in the same orbit with the same radius. Tell me about the period. Is the period of this spacecraft greater than, less than, or equal to the period of the first one? And then explain your reasoning. All right, so let's do a little poll in the chat here. Should this second spacecraft have a period that is bigger, smaller, or equal to the first one? And then explain your reasoning. So let's just do the poll for what do you guys think? Greater than, less than, or equal to? Okay, I've got one vote for equal to with a question mark. What else do we have? There's another equal. Okay, that's good. Good, good. Another equals. Okay. Yeah, you guys are all exactly right. This will be perfectly equal. Okay. And now explaining your reasoning, I'm going to steal basically what Rhea said here. They must be equal because T isn't dependent on little m. Okay, there is no little m in this T equals 4 pi r cubed over GME. Nowhere in here is the mass of the spacecraft. Okay, the radius and the speed and the period and stuff depend on the radius, the universal gravity constant, and the mass of the planet you're orbiting. So as long as we're not changing the size of the circle or the mass of the planet, the period's going to stay the same in there. All right, this one gets you a whole whopping +1 points because, well, I think they need to skimp on points somewhere and they chose to do it there. So, yep. Okay. And the last part to this question, we're taking that spacecraft and we're now throwing it into a bigger orbit. Are we going to go faster, slower, or the same as the speed we had before? Okay, so we take this spacecraft, we move it to another bigger, stable orbit. And are we going to go faster, slower, or the same? Explain your reasoning. All right, so same deal in the chat. Greater than, less than, or equal to. Let's see what we can think about for ideas there. Okay, so I've got 2 votes for slower. Three votes for slower. Yeah. All right. So, yeah, this one will be going slower as well. Now, let's talk about why. Okay. I'm going to go back to the derivation because that's the easiest part here. And go back to this orange line I just circled here, this part right in here, that says that v squared is equal to g times me over r squared. Right? This means, because we're not changing the mass of the planet we're going around, as the radius increases, the speed must decrease. There is an inverse relationship between those two variables. Right? And that's the reasoning here. And you can say it simply as this is slower because there's this relationship we found. It's opposite. Okay, so larger r. Something like that. Or you could just say, larger radius means smaller velocity. See the relationship in part B. That's perfectly fine too, to say, hey, it's already answered in this other part of the question, sort of stuff. This part, again, gives you a whopping +1. So, yeah, the majority of the points for this question came in the free body diagram and in the math in there. And that is fairly typical for at least this kind of question, where they're going to give you a lot of points for the foundational stuff and then a few points at the end for the explanations and the patterns. Will that hold true for this year's? I don't know, because part of me is thinking with this year's exam being much more open book and they can't check to see if you have anything sitting in front of you, they will be much more probably stingy on the easy freebie points and giving more points to the explanations and the effects and stuff like that. So probably putting more points into things like part B and part C and less points into part A, honestly. But who knows? I won't see that scoring guide until, well, after the exam. So kind of my guess on that one. Yeah, so the idea with this year's AP exam is because there's 2 questions and because there is no way for us to monitor what you are doing at home, they are assuming that you could have your textbook sitting in front of you and your notes from the class sitting in front of you and any other internet sort of devices on there. So if you're doing this on your phone, you've got your laptop sitting next to you or vice versa. So they're really going to try to hammer the stuff that you can't just look up. They're not going to ask you a question like saying, oh, what is the force that is pulling this thing in a circle? Because that's a lookup question. That's a basic general knowledge question. What they might ask you is, okay, what happens to the size of the circle or the speed of the object if I make the mass of the Earth bigger? Or how does the radius of the circle impact the period? Or if I want to double the period, what does that mean I have to do to the mass of the Earth or the radius or something like that? Those are the kind of questions that I'm going to expect a whole lot more of, simply because those you can't just look up. They're not an easy textbook sort of answer. Also, because of the kinds of questions they chose, pretty much any answer you're going to put down, don't be surprised if there is a explain your answer or explain your reasoning or stuff like that with it too. Okay. All right. So we did that one. Second question. Actually, any other questions on gravity before we jump on to the next part? All right. So the next question, we're skipping question 2. Question 2 on this 2018 FRQ was about electricity, which is not on this year's exam. If you're interested in it, I did put it in the slides and a link to the answer key and stuff like that for it. We're just not going to go over it right now. So question 3, this one talking about a disk spinning about an axle in its center. Student does an experiment, shows that while the disk is spinning, there is friction that exerts a constant torque on the disk. So a constant torque on this disk going on here. All right. Without reading any further here, what topic or topics are we going to be talking about with this question? Yeah, good job, Corey. Yeah, this is 100% rotation. Okay, which means, at least from so far, it looks like it's just all rotation. We might also see something about forces or something about energy in here. But really, this is the big idea here. And yeah, so this is where I would pull up my rotation notes or open my textbook to the rotation section or look into the rotation part of the reference table and start seeing what the heck is going on here. Yeah, dynamics, kinematics, I'm going to kind of lump it all together in being rotation in general. I really don't distinguish when I teach it between rotational dynamics and kinematics. I kind of lump it in. This is all rotation stuff. It's all moving things in there. But yeah, it definitely reading a little bit more ahead, kinematics, momentum, that sort of stuff like that could come in there as well. So definitely. All right. So we know we're looking at rotation. We grab our rotational references and tools and start thinking through that sort of stuff. So part A, at time t equals 0, the disk has a counterclockwise, positive. Good to know they are telling us what we're considering positive. So as long as we're rotating counterclockwise, that is a positive direction that we're talking about here. Okay. This disk then comes to rest at some later time t1. On the grid below, sketch a graph that represents the angular velocity as a function of time from t0 until t1. All right, so, well, I guess we're going to sketch a graph. So let's start with the easy part here. They tell us that we start at omega naught at time 0. So I know I have a point right there at the beginning. And I know we come to a stop. So I must have a point at the end. And now the big question is, how do I connect those dots? Is this a line? Is this a curve? If it's a curve, which way is it facing? That's the question for this part. All right. So let's ponder this. So I've got a curve up. So 1 vote for something like this as we go through. And that's a possibility. Any other votes? Or do we just want to discuss and go from there? Because we could have it be linear, or it could be a curve down, sort of thing like that. So kind of our 3 options in there. Wait, no, linear, misread the graph. Okay. All right, so we kind of have all 3 options in there brought up. So let's talk about what's going on here. And I'm going to do big picture. Yeah, okay, so now we're reading through the question. And the idea here is that this torque is constant. A constant torque means that we must have a constant acceleration. And a constant acceleration means, yeah, it's a delta V, or sorry, delta omega over t is constant. This should be linear. All right, so we're expecting this to be perfectly linear with a negative slope. Okay. And by getting that one, we kind of also got the other one here. Our angular acceleration has to be a straight line in the negative region, constant and negative. Okay. The nice part about this is it doesn't matter where you put the angular acceleration, as long as it is horizontal and negative. So you could put it at any point you want to, but this must be negative. They didn't give us enough numbers. In fact, there are no numbers on here for us to even determine where it is. But that's pretty much what it is. All right. So this part gives you a whopping 4 points. Again, I would not expect this many points from this year's exam. But basically, they give you 2 points for the angular velocity graph, 2 points saying that you got the endpoints correct and it's a negative linear graph, and then the angular acceleration, constant and negative. So that gives you 4 points out of that. Questions on the graphs before we move on, because this is kind of the important part. Okay. Well then, moving on. Part B, kind of short. The magnitude of the frictional torque is tau naught. Derive an equation for the rotational inertia of the disk in terms of tau naught, omega naught, and T1, and any other physical constants you need. All right. So I'm seeing torques, moment of inertia, omegas, and T's. We're supposed to derive stuff. There's 2 ways you can derive this equation. And I will walk you through both of them because you get to choose what's going on here. So starting off, let's do I guess, my preferred way of doing it first. And that is to use Newton's laws. Okay, saying that sum of the torques is I times alpha. Right off your reference tables, nothing fancy with this. We're also going to pull in the fact that alpha equals the change in omega over T. So this would mean that my torque, T naught, is equal to I. My change in omega is really just omega. I suppose if we're being really exact here, negative omega naught over T. Okay, so kind of just doing this, that moment of inertia is the torque times the time over the initial velocity. That is one way to do it. And that's probably, like I said, my favorite, my easiest way of doing it. Because, I don't know, for me, it always makes sense if you're not sure where to start with the Newton's law and go from there. All right, questions on that part? Okay, the other way to do this question comes from the fact that a change in torque changes my angular momentum. And this is not one that actually, let me write it out like your reference tables have it, that I normally use. Because, I don't know, angular momentum is just one of those weird things I try to avoid as much as possible. Kind of like impulse and momentum. I'd rather do forces and accelerations than impulses, but that's just me. This also works. L, angular momentum, is moment of inertia times velocity, angular velocity. So our change here, this would all be negative. We end up with the same thing, that I would equal the negative torque times T1 over a negative omega naught, which works out to be the same exact thing. T naught, or tau naught, T1 over omega naught. So exactly the same outcome, 2 different ways of looking at it. And really it depends. Are you thinking in terms of forces and torques or angular momentums and torques? But it's the same exact answer, regardless of which way you do it. Okay. This question gets you a very nice 3 points in there, which is not bad for a pretty straightforward derivation. This one's a lot more linear thinking than the gravity one we had to do before. At most, we pulled 2 equations together. We didn't have to pull 3 or 4 different concepts out of our hats and stuff like that. So that's kind of nice that this derivation was a little bit quicker. And also, just to point out the negative signs here, the torque is negative because it's slowing down the disk. Omega naught's negative here because this is really the change in angular momentum, or just like it was the change in velocity in the alpha side. So that's where the negative signs come in. They all disappear. So they're all gone. But yeah, that's kind of the gist of where we're going with that. All right, part C. In another experiment, because we can't have enough experiments in science, a student is going to drip oil on the pan. So we have our same setup. Let's go back for a second. We have the same setup with the same spin as before, but now instead of just letting this thing slow down by itself, we decide it's time to drip some oil on that pan at t equals 1/2 T1. So we're going to start reducing the friction halfway through this experiment. Okay, as time passes, more and more and more oil reaches the surface, which reduces the friction even more. So we start off with the whole amount of friction for halfway through this experiment. Then we add oil, which will reduce the amount of friction as we go through. And we have to make the same two graphs in there. All right. Let's, well, I guess. Yeah, that's kind of what I'm thinking, Relo. Or Ria. Wow, I can read names. Basically, we need to be linear for the first half, right? Not much is going to change there. This is a terrible line. We'll see if I can do better. That's a better line. So this part, still linear. For at least the first half. And now, what's the oil going to do? The oil reduces friction, which means that our torque goes down, which means our acceleration goes down, which means, yeah, we should see some sort of abrupt curve going on here. You're right. It won't reach zero because we are looking at some speed left over, because the T1 is when it reached, T1 is when it stopped with full friction. We took away some friction, so it should still be spinning a little bit after that. So we're looking something kind of like this in there. So yeah, so linear for the first half. Then we've got concave up curve. And again, mine is fairly abrupt. You could make that very or more shallow change, and that would still be fine, as long as it's obvious to whoever's looking at this graph that your slope changes. You go from being linear to non-linear to being a concave up sort of thing going on there. Okay. That graph itself gives you 3 points. You get a point for basically those three parts that we labeled here. So linear until T1/2, then concave up, or somehow slowing that up, showing that our rate of acceleration has decreased, and then not having it hit zero at or before T1. Right. The second chunk to this, the acceleration graph. Yep, pretty much. It's going to, starting off the exact same as before. Now, I'm not going to be clairvoyant about this, but I would try to assume, I'm on the load page, that whatever you made your acceleration be in the first graph for part A should be the same as you make your acceleration start off as for point C. We haven't changed any of the friction or anything else beforehand for that T1/2 part. And while the scoring guidelines for this one aren't saying it has to be exactly the same, this year's might be. So just consistency in your graphs is a really good thing to keep in mind too. And then after T1/2, our acceleration becomes less and less and less. This is going to be linear, probably. Actually, I put linear question mark in there because I'm kind of assuming something here, and I don't want to. That assumption may not be true. I'm assuming that the oil reaches at a constant rate, meaning my change in torque is actually a constant change. But really, this could also be a curve. Let me do a different color just to point it out here. This could also be something like this, where you curve it up. That's fine too. As far as we know, we can't say. We can't say whether this reaches 0 or not. All we can say is that if this does reach 0, then it should stay at 0. But there's not enough info in the question to really make a claim about whether it reaches 0 or not. So I would say as long as you're consistent in what you're saying, it's fine. So if you have that line reach 0, then just plateau it off and keep it at 0. If you don't have it reach 0, that's okay too, as long as this second half actually does change something. The acceleration graph gives you 1 point, because all they're looking for here is that you have a changing acceleration in that section. That's all they're looking for. I suppose if they had more points to give, they could give you a point for keeping it constant for the first half, but they don't. So that's kind of what we got to work with. All right, questions on this one? So why is the velocity graph concave up instead of concave down? I need the slope of that graph to be negative. So if I'm looking at here, I need to have I have a negative slope. I need to have a negative slope, and getting pretty close to 0 on there. If I did this as a concave down, that would mean my slope gets positive, less positive to 0. This would mean speeding up in that case. So if I suddenly had to drop down, is this making sense? I feel like I'm kind of saying this backwards. If I were to draw it as linear and then concave down, that's a slight change, and this is a larger change, meaning that somehow my acceleration got bigger later on in this, which is not what's going to happen. So, okay, good. So second explanation works better there. Okay, so it's all about the fact we should have less acceleration at the end than we do at the beginning, which means that our change in V has to be more minimal throughout that. All right. Okay, and that kind of ties into this one here. This is the last part of the question. The student is now trying to mathematically model this thing going on. The student writes down 2 equations for the time bigger than time 1/2. So we're looking in the second half of this experiment, not with the constant friction, but now with the oil dripping on the pan changing friction part. So they're saying that either equation 1 or equation 2 is a good model for this situation. Which one do you think is the best option? And why is the other one wrong? So we need 2 parts here. So why is a certain equation good and why is the other one not good? All right, so ponder for a second, then we'll go over it. All right. So we've had a little bit of time to ponder. What are we thinking? Equation 1 or equation 2? Which one's a better option for modeling that graph? All right. Yeah. So in general, I'm just going to write this out here. Equation 1 shows that the torque increases as time increases, right? It's t minus 1/2 t1. It's time minus some constant in there. So as that time term increases, that C parentheses term, this guy right in here, is going to get bigger and bigger and bigger. So yeah, this one basically says the torque goes up as time goes up. Equation 2, that says the opposite. Okay, which one of those two, now that we kind of reworded what's going on, should the torque go up the longer we wait, or should the torque go down the longer we wait? Yeah, the torque should go down. Yep. And there is my reasoning for it, but it is equation 2 is good, equation 1 not so good. Okay. Unfortunately, this question only gives you 1 point. This sort of question right here is one that I would say for sure is much more likely to show up on this year's exam, worth more than 1 point. Taking some sort of model or some sort of mathematical thing and saying this works because is really, really, really likely. I can't say 100%, but this sort of thing. So why is the torque decreasing again? Okay, so let's go back here. So the torque is decreasing. Remember, torque is force times radius that's perpendicular. The force in this case is the force of friction times the radius. The radius doesn't change. So as the force of friction decreases because oil, therefore the torque goes down as well. Okay. All right. Other questions on this question number 2, question number 3, whatever question we're on here. This part especially. Okay. Well, if it's nope, then we're on to our last question. By the way, looking at our time so far, we've been doing a pretty good job of getting these questions done in the suggested amount of time. And that's fairly typical for what you're to see on your exam coming up in a month or so. You've got a 25-minute block, which basically was the second question we just did. And you've got a 15-minute block, which is basically the first or this question that we're doing. So we're doing pretty good on time as well. We're not taking crazy long amounts of time to get through these either, which is nice. Okay, the last one of these, we're skipping question 4. Question 4 dealt with waves. Waves is not part of our exam this year, so we're kind of putting it off to the side and saying we'll get to it later in here. So let's look at question 5 here. We have block P. It has mass M. It's on a horizontal frictionless surface, no friction, attached to a spring with a spring constant K. The block is oscillating with a period and an amplitude. We drop a block on top of it. Okay. The block sticks to the top of block P, and then it oscillates with a new sort of stuff. All right. Topics for this one. I think there's probably 4 that you can think of off the top of your head for this. Yeah, so we're talking about springs. So this is probably some sort of spring, simple harmonic motion sort of stuff. This might also be springs with energy, depending what's going on. Yep. Springs, energy. What else? They talk about sticking to something, which is momentum. And maybe not. I'm not quite sure about this part yet, but we may get into forces too. I'm not sure about that part, but definitely energy, oscillations, momentum. Big 3, maybe forces. That's my 4th. We'll see how it works in there, but those are my big ones right there. All right, so part A, determine the numerical value of the ratio period PQ over period P. All right, so this is one that's very nice because it's pretty much just a reference table lookup. On your reference tables, they tell you the period of a spring is 2 pi square root of m over k. So our ratio TPQ over TP is going to be 2 pi square root of PQ is when the 2 blocks are stuck together. So I've got to use their entire mass. So that's 3m over k over 2 pi square root of m over k. And because math is nice and fun, we get to cross off all the stuff like that. And we're left with square root of 3. So why is there 3m? So for TPQ, period after they collided, their masses are stuck together. So this would really be, so the total mass on that spring now is 3m instead of just m. All right. This, if you're keeping score at home, this is worth 1 point. And honestly, that's probably about what it's worth. There's not a ton of things you need to do on here. It's a lookup off your reference table for the equation, and it's plugging in a couple numbers. So that's probably fair, actually, for that part, to say it's only worth 1 point. Now we get into the meat of the question, and that is, whoa, where's the rest of my question? Oh, no. Oh, no. Pause. This is not good. Where's my question? Pause for effect. Hold on. I got to go save our question here. There we go. Okay. Snipping tool. Snip. Steal this. There we go. Copy it. Get back in here. Where's my paper? There's my paper. Paste. All right. So back to this question. This is the new and improved question. Are you in the right spot too? Almost. Okay. So we just did this part going through, and now we have the same figure. We have the same question. We're doing the same thing, but now we're talking about amplitude. We are not talking about period anymore. Amplitude, the motion, how much of this is going to be the motion sideways here, how much of that is affected by the dropping another block on it. Okay, and we got three choices, but they do want this one wonderful paragraph length response thing here, which means it's not going to be as simple as saying it's bigger than. Okay. This is also worth a grand total of 6 points. This is where the majority of the points for this question comes in. And this is exactly what I would expect on your exam in a month too. Maybe a little warm-up point question, and then go into getting a lot more points in there. So amplitude of this motion is talking about energy. Okay, the bigger the amplitude, the more energy we have. And thinking this through, if I have this block land on it, should we end up with more energy or less energy as a result? All right, I got a couple mores here. So why? Why are you thinking there's more energy in this now? Okay, so there's kinetic energy, right? Kinetic energy is 1/2 mv squared. That's perfectly true. In fact, we're going to jot that down because that's going to be important later on. Kinetic energy equals 1/2 mv squared. Good point to look at here. Okay. I like where you're going, but we got to add one little tidbit in first. Going back here, the blocks, again, stick to each other. And if they stick to each other, that's an inelastic collision by definition. And if it's inelastic, that means we lose some kinetic energy. Okay, so the total energy here is actually going to be less than it was before we dropped that block on it, because we are losing some kinetic energy. And that kinetic energy at our equilibrium point must equal the potential energy in the spring at our amplitude. So if I have less kinetic energy to begin with, I have less amplitude going on in here. So we should end up with less overall. Let me try to type out that paragraph, and we will see where we go from here. Okay. Because paragraph length responses are fun. Okay. Okay, so starting off, there's my claim. I am saying that the amplitude will be less afterwards. So we're going to take that. We made our claim. Now I'm going to go through fundamental principles here. This is conservation of energy. This is potential energy at the extremes, at the amplitude point. must be equal to kinetic energy at the equilibrium point. At the max amplitude. Okay, so that's kind of wordy, but I think that hits all the points in there. If we wanted to, we could also do some math behind this. It's not wrong to do that. Actually, that's probably a good idea. Let me add another page to this, and we'll actually go through the math behind this part too. That screen's a little blurry. Interesting. I wonder why. It does look a little fuzzy. Oh, interesting. All right, I'll make sure I throw the PDF of this on as well, and hopefully that's clearer and easier to read off of too. Okay, but let's go through the math side of this too. If you're not a word sort of person, but you want to do your paragraph length response with some mathematical backup to it, we could do that same thing too. We can say that the kinetic energy must be equal to the potential energy in the spring. So 1/2 mv squared equals 1/2 kx squared. So x, our amplitude, must be equal to halves disappear mv squared over k, which in our case is 3m because it's the, actually, we'll just leave it like that. Okay. The other part here is we need to find v. So that's a p before equals p after. So we can say that beforehand we had mvi. Afterwards, we have 3m because we added the blocks together times vf. That means our speed at the end after this collision must be equal to the initial speed over 3. So now we can say that x before, or our amplitude beforehand, would be mvi squared over k. X after will be 3m vi over 3 squared over k. 9.3. So comparing those two, the amplitude before is 3 times the amplitude afterwards. And therefore it's less too. So if you want to walk through the verbal math behind that portion and talking about, hey, this is conservation of energy. We're talking about potential energy turning into kinetic energy. We're at the equilibrium point, so we have max kinetic energy, stuff like that. And because we have a collision, we're doing P before equals P after. Combine them together and get to your answer there. So either way, paragraph, mathematical, words, no math, or math, less words. Either way is going to work, but you do need to have a paragraph. You need to write something about this in there. Okay. In fact, I've got snipping tool open. Let me actually paste in the AP's scoring guidelines example here. just so you could see what they say a good response would be to that question. Okay. And they kind of split it both parts there. So there's another way of writing it. So on there, Robert, yeah, I'm going to upload this to Findable as soon as we're done with the stream, and you'll be able to get to it from that site as well. So definitely you can watch this as many times as you feel like. Okay. All right, so it's like 2:10 right now. Any other questions on this, or are we good to go? All right, cool. If you guys have questions, feel free to shoot me an email. My email is going to be in the chat in a second here. So feel free to shoot me an email about stuff like this, or I will see you guys in the next stream, which will be, again, either tonight or Wednesday, same time, same place. All right, have a great day, and I will, see you guys all later.